Good morning, my dear students. In this session, we will discuss about an example problem on two-hinged stiffening girder. So, already in the last session, the procedure for stiffening girder, two-hinged stiffening girder problem solution is being discussed, and I'll just go through it once again in a quick way. So, we wanted one extra equation because the number of unknowns are 3, but the equation that we are able to write are only 2 for the two hinged stiffening girder. So that's why we have made an assumption that the total load acting on the girder shall be distributed equally to the stiffeners, nothing but the no, the vertical members connecting between the cable and the stiffening girder. Okay, so that's how it is. Total load divided by total span of the girder will give you equivalent UDL. So this needs to be calculated in this approximate manner. Okay, then only we will be able to solve the two hinged stiffening girder problems. Otherwise, it is like an indeterminate structure where a number of unknowns are more, number of equations are less. Reason, when you compare this with three hinged stiffening girder, you have three equations and three unknowns, like Q naught, VA dash, VB dash are the unknowns, and the equations are sigma m0, sigma fy0, and mc0, where the third hinge is present. Now in this case, you don't have third hinge. That's why we need that extra equation. That's why we are taking a condition or assumption, we say, that the total load on the girder shall be equally distributed onto the total span of the girder. Okay, right. So now let's see the problem now. So these are all the, we have two examples here. One appeared in October 17 as well as May 18. Two times it appeared. And one example I have given you to for your practice. Okay, so let's solve this one, the university question, right? So a two-hinged stiffening girder span 100 meters and the central dip or sag 10 meters, subjected to 2 point loads, which is 200 kilonewton and 400 kilonewton at 20 meters and 80 meters from left support, respectively. Okay. So what we need to find is find the shear force and bending moment at 25 meters from left end. Okay. Also find maximum tension in the cable. So these are all the questions that we need to solve. So let us see that the diagrammatic representation of the given data: span 100 meters and I mean to say sag or dip 10 meters, loads 200 and 400, 20 meters from left and 80 meters from left. So if 80 meters from left is equal to 20 meters from right. Okay. So these are all the suspenders or nothing but stiffeners, so you can say. Okay. So where A and B are the hinges for the cable, and whereas A dash and B dash are the external hinges for the girder, two hinged stiffening girder. Now if you observe, we don't have uh, any hinge at no location C dash. We don't have hinge at C dash, the center point of the middle of the girder. Okay, right. So now we start the calculation with WE. Okay, because we want this assumption to be applied first. So the assumption must be applied first, the what we actually have thought of the assumption what is taken first. Okay, so assumption must be applied first. So equivalent UDL, your first calculation is to calculate equivalent UDL. So what is that? Total load acting on the girder. What is total load acting on the girder? 200 plus 400. Okay, so 200 plus 400 is the total load divided by total span of the girder, 100 meters. So total span of the girder, 100 meters. The total 600 divided by 100, it will be 6 kilonewton per meter. Okay, right. So once we get equivalent UDL, then you go for calculating H value, which is WL square by 8H. Horizontal thrust or nothing but horizontal reaction. Okay, so WL square by 8H. W is 6. So in all the cases, what we need to use is only equivalent UDL, whereas you can't find the actual UDL acting over there, right? So WL square by 8H. L is 100, H is 10. So that comes to 750 kilonewtons. Okay, got it. So all these no unknowns are for cable. Okay, that you should get my point. Because what is the reason to take cable first against the uh, two hinged stiffening girder, where in case of three hinged girders we started with girder free body diagram, right? Whereas here we don't need that, because the assumption that you make here will get your UDL value directly, so we don't need to use girder first. Whereas in case of three hinged stiffening girders, you need to first solve girder, then only you are able to go for to take up the cable. Reason, unless otherwise you solve for Q naught value, you can't move to the cable. Okay, where cable, if you take straight away first to solve, Q naught is unknown for you. So first take free body diagram of girder, three hinged stiffening girder, solve for Q naught, then come to the cable. Whereas here we don't need such no to take first girder. So we will straight away take the cable free body diagram here. Okay, so take cable FBD straight away, then solve for all these unknowns. So apply first assumption. So you get equivalent UDL. Okay, so see here, and this is the now cable that you have. Okay, so all these stiffeners are nothing but suspenders. The load coming from suspenders onto the cable is in fact Q naught, whereas in case of two hinged stiffening girder, it is W suffix E. Okay, so once you know this value, W by L, you can calculate all these reactions. H, HA equal to HB, that's why I'm just taking this as H. So VA and H here and VB. So all these reactions are you are able to solve because WE we are calculating straight away in the initial step. Okay. So what is H for UDL cable acting with acted upon by UDL? It is WL square by 8H. So we got H value. So VA equal to VB equal to, this is UDL. So W into span is 100 by 2 is the reaction. VA is equal to VB because it is symmetric. So 6 into 100 by 2. So 600, half of the value, 300 is the support reaction. So once you get these two reactions, and TA, TB means the tensile force at A, nothing but resultant at A, and tensile force at B, nothing but uh, resultant at B. Okay, resultant nothing but square root of horizontal force square plus vertical force square. Okay, so that will give you 807.8 kilonewton. Okay, so this is the T maximum value. T minimum will occur at center C, and that is equal to H. This is if you want to just identify what is minimum tensile force. Okay, right. So that's all with the cable unknowns. So unknowns in the cable are equivalent UDL, that is found from the assumption. Equivalent UDL is found, then horizontal thrust is found, support reactions H, VA, VB are solved, then finally internal forces, maximum tension and minimum tension. So this is the cable solution. Then come to the girder. So girder has got VA dash. This is now if you remove the support A, you'll have VA dash, VB dash. Okay. So upward UDL WE, that is equal to 6 kilonewton per meter as already applied by the assumption. Okay. So you have applied the assumption, so that will give you equivalent UDL value 6. Okay. So it is only enough to use just two equations to get VA dash, VB dash. That's all. So two equations are nothing but one moment equation and one force equilibrium equation. That's simple it is. Okay, straight away if you take moment at A, you will get VB value. And if you take sum of vertical forces 0, you are going to get VA dash value. That's it. Okay. So that's how it is. So taking moment at A0, VB upward load, upward reaction I have assumed. So this into 100. So considering anti-clockwise positive, I have noted it here. Okay, and this is also anti-clockwise moment from UDL. So 6 into 100 into the distance 50. Okay, 6 into 100 into 50. And these are all clockwise, so minus I wrote 200 into distance 20 and 400 into 80. Okay, is equal to 0. So that will give you VB dash is equal to 60 kilonewton. Positive means the upward reaction, that is what is given is correct. Then sigma of y0. So VA dash upward plus VB dash upward plus 6 into 100 UDL upward minus 200 minus 400 is equal to 0. So VA dash is equal to minus 60. Okay. So this direction should be downward. Okay. Got it? So here, if you clearly observe that because of the assumption, you are getting VA dash and VB dash values equal and opposite values. Reason already 200 and 400, because of this 200 and 400, you got this UDL 6 kilonewton per meter. Okay, so already this 400 plus 200, 600 is balancing 6 into 100. 600 is it is balancing. So VA dash and VB dash should have a balancing value. So if it is plus 60, this should be minus 60. Then only sigma Fy will be 0, because already 400 plus 200 minus 600, it is 0. Okay, total vertical force is equal to 0 already. Okay, why? It is because of your assumption. So we started with that assumption only. Whereas in three hinged stiffening girder, this is not the case. You got some VA value, a VA dash value, and you got some VB dash values. Okay, there, this situation is not there, right? Okay, so that you can observe it here. Why it is one is plus and another one is minus. Okay, right. Another one more part of solution is left, that at a distance of 25 meters, okay, from left, find shear force and bending moment. Okay, so that you need to solve. So 25 meters from left, this is 20. So roughly, you take a section here, 25 meters. Sum of all the forces to the left or to the right. So this downward 60 here. Okay, so minus 60 and minus 200 plus is upward. So left upward and the right left up, right down is positive. So plus 6 into is 6 kilonewtons, and into the span 25. So 6 into 25. So shear force is minus 110 kilonewtons at 25 meters. Same bending moment also. So this is left anti-clockwise, hugging minus. So minus 60 into distance 25. Okay. 200 into 5. This distance is 5. This is also anti-clockwise. So minus 200 into 5. This is clockwise. Okay. So clockwise positive. So 6 into 25 into, this is UDL, right? So 6 into 25 into 25 by 2. This is like upward UDL, not the downward UDL. It is like upward UDL. Okay. So total load will act at center of 25. So 25 by 2 is the distance. That is minus 625 kilonewtons. This is only at this location. Whereas in the earlier case, you have drawn SFD and you have drawn BMD for the complete beam. Okay, same can be done here also, if at all that is the question. Okay, so this is the solution for this problem. I'll just go through quickly once again how we have solved this one. Okay, so you don't have to solve three equations and three unknowns here to find out. We have assumption, a simple assumption straight away, that the UDL, that this UDL acting on this main cable as well as this stiffening girder can be easily found as equivalent UDL. It's nothing but total load on the girder by total span of the girder. So once you get this value, then straight away take the cable free body diagram and solve for horizontal reaction, vertical reaction, as well as the maximum tension. Same here, horizontal reaction, vertical reaction, as well as the maximum tensile force. And minimum tensile force will always be at the maximum sag point or dip point. So that is about cable solution. Then come to the beam. Okay, then you have only two unknowns, VA dash and VB dash, because already WE is a known value both for this as well as for this also. Okay, so this is if you cut all these cables, okay, but this is the nature of load that the internal force that the stiffeners or the suspenders will have. Okay, load like this. So this is upward UDL for this, and this is downward UDL for cable. Okay, so remember, uh, for cable it is downward UDL. For girder it is upward UDL. Okay, so when you join the cables, it will be again you can't see it. Only when you take a section, you can see the internal force. That internal force is WE. Okay, right. So VA dash, VB dash are the unknowns in the girder. So use two equations, maybe sigma M0 and sigma Fy0. And if at all, if you are asked for shear force bending moment, you just calculate it as a beam, just like simply supported beam. Okay, right. So this is all about the unit 3, cables and suspension bridges. So practice this problem. I have given an example problem, a suspension bridge span 80 and now width 6 meters is having two cables stiffened with two hinged girders. Central dip is 8 meters. Okay, so the suspension bridge, full bridge details are given. Dead load 5 kilonewton per meter square, live load 10 kilonewton per meter square, which covers the left half of the span. Okay, so dead load is for full span because the beams are the pathway or carriageway will be of full span. And 10 is only for left half span. So find shear force bending moment at 20 meters from left end. Also find maximum tension in the cable. Okay, so you just need to work out this problem in terms of you have to first formulate this problem, then only you can solve it. Okay, right. Thank you.